We are talking about core sampling. I'm Christian Pimentel. This is Alexandria Gaines. This is Sean Peer. And this is Angelis Jones.
This picture is putting in detail what they do as a core sampling. They slice a piece of the earth to try to try to see where the oil is. Yeah, like trying to find the oil and
What is core sampling? Core sampling is a process in which geologists take a piece of earth and slice it into search of oil. Like they'll take for example, offshore oiling, they'll take a drill and they'll bring up oil and then they'll take it apart and then go slice it up to find the rock of the oil inside of it.
And these pictures show, this one is an underground, where they were drilling underground, and it shows the pipe and they're sucking up some of the earth to see if there's any oil. And then this shows just a man holding the pipe as it came from drilling.
right there is like a big chunk of it is like pieces of the core sample.
And it presents of our core sample.
I'm Micah Dermott, Juan Rubio, Jason Enriquez, Joel Torres, and Christopher. This experiment is over core sampling, and what we have here is we have some light colored sand, we have darker colored sand, soil, and gravel. So what we're going to be doing is we're going to be making the layers of the earth in a cup. Go ahead, man. This is our first layer. And we're going to measure out about 2 centimeters of soil right here. We'll just do one, keep going. More, just faster. Alright, so that's our first layer, and we're going to go ahead and do our second layer, which is the darker colored soil.
Oh, we have to
dampen it. Alright, now for the darker. Keep going. Alright, stop. Alright, now our next one is going to be gravel. I'm going to hold it on the dampness. And now we're going to do gravel. Joel, you want to spray that down? And now soil. Try to get your finger. There you go. Alright, yeah. So this is now our layer of the earth, and we're going to need 3 volunteers to come do something for me. So DeMarcus, Ivan, and Angelique, please. No, you're not tasting it, don't worry. Alright, so one at a time, each of you are going to come in and you're going to put your straw as far down into this as you can. Once you do that, place your index finger over the top of the straw and then pull it out. Keep it there so everything doesn't fall to the floor. Just as far down as you can. No, you gotta let the air up first. Now, there you go. Keep going next.
So it's not that easy to just go straight down, is it?
Yeah, you have to get, it's gravel.
Alright, well, what we did here is this represents when people go in with, the companies go in with the drills and they dig into the ground and then they use the pipes to extract the different layers so they can see what all is there. And some of what happened here is sometimes they don't get anything at all when they go down, things could fall out. Or if you, sometimes they go down too far, they go down into the cap rock, this layer, the rock layer right here, and it can bend the pipe out, and then you got a broken pipe and no samples. And then, or you can get what Angelise has, and she actually did get some. If you look really close, you can actually see some of the layers. You can see the lighter sand and the soil. And that's from where she went through the rock, and when she pulled it out, some of the rock pulled some of the stuff out. So, I believe that concludes our experiment.
I'm Joshua Martinez. This is Ivan Lopez. This is Vigo Noriega, Kyle Goodman, and Samantha Harmon. And we're going to be talking about porosity and how it is related to oil and natural gas.
Okay, this is the bore samples, the samples that they take from the ground to find the oil. They take the ground samples going down to see what was their use. They usually can bring up the bore samples. They bring up the samples of the dirt, and then these bore samples usually is used for the porosity. The rock with porosity usually brings it up along with the bore samples.
Porous rocks are rocks that have little holes inside of them that could hold oil or natural gas down beneath the Earth's core, and what they do is they blow water through them so they can get the oil and natural gas out. So, and Rigo and Samantha.
So porosity, we just explained at the end how liquid could flow through rocks is the permeability, and porosity is the amount of how much water the rocks could hold in the holes. Porosity and permeability they're related.
Okay, my name's Ivan Pedroza.
My name's Alec Davis.
Danny Lugo. Get the Marcus Wilson.
And our experiment was over porosity. Okay, can everybody get out their porosity sheet? Experiment, we're testing the porosity of different sized rocks. First, we're going to test the porosity percentage of large rocks, then medium rocks, then small rocks. Okay, so let's get started. We're going to pour 350 milliliters of rocks into this beaker. Don't want to just pour them in there because I don't want to crack or mess up the beaker. Okay, so that's about 350 milliliters of large rocks. Now the Marcus is going to put water to cover the surface of the rocks. That is 100 milliliters in there already. Okay, now it's just above the rocks, and we have about 3 milliliters of water left. So we poured 197 milliliters into there, and you guys should record that, or you guys record it under volume of water poured, 197 milliliters. And then, or volume of material, I already told you guys that. I don't know if you recorded it, but it's 350 milliliters.
For a large gravel?
Yeah, for large gravel. And now Danny's going to pass out calculators. so we can do the math. And as you guys can see, it shows the equation on there. Everyone put in the milliliters into your equation, plug it in. Okay, can I see a calculator? Are there any more? $197 divided by 350 equals 0.56 times 100 equals 5.6. So 56%. It's 56% porous, or the porosity is 56%. So we're done with the large gravel now. Alex is going to take the medium gravel. He's pouring the same amount of the gravel, 350 milliliters, so you can record that now. The volume of the material is 350 milliliters. Is that enough? Okay, there's 350 milliliters of material in there. Now DeMarcus is going to do what he did again by pouring the water just above the gravel. Alright, stop. Okay, he poured about 40 milliliters, 140 milliliters, because the difference in the large gravel and this medium gravel is fairly high, because the medium gravel is a lot smaller and it's a lot more compact than the large gravel, so it takes less water to fill it. And so 140 milliliters of water
divided by 350 raw material equals 0.4, and you times it by 100 and you get 40%. And now we are about to use the small gravel.
About 350 milliliters of the material. So once again, it's the same, so record 350 milliliters. And DeMarcus is going to put water just as he did in the other two. Stop. No, that's enough. Okay. 174 milliliters of water are in this one. So once again, we're going to use the same equation.
So it's going to be 174 divided by 350 equals 0.49 times 100 equals 49%.
And this wraps up our experiment.
Alright, well, my name is Theon Jones.
I'm Thomas Banks.
And today we're going to be showing you the Cartesian diaper experiment. Now, first off, we're going to need materials, and that will be 1 straw, 2 large paper clips, 1 rubber band, a water bottle, and a cup, and water. Now, first we're going to start off by folding this straw in half, and then we're going to secure the ends of the straw with this rubber band. And this might take a while. So now that the ends have been secured, we're going to add paper clips to the sides of them just to increase the mass a little. Now we cut the straw a little bit, that's what the scissors are for. And when we drop it in there, you notice that it floats. That's without adding any pressure to it. Now when we put it in this bottle here, you notice it still floats. Now, without squeezing the bottle, the overall density of the diver is slightly lower than that of the water, so it floats. When you squeeze all the sides of the bottle, you increase the pressure of the air bubble, compressing it into a smaller space. Now, this decrease in the volume of the bubble causes an increase in the overall density of the straw. When it becomes greater than that of the surrounding water, it sinks. Now, and releasing the bottle will cause a decrease in volume of the bubble and an increase in the overall density of the straw. When it becomes greater than that of the surrounding water, it sinks. Releasing the pressure allows the air bubble to expand back to its normal size, and the straw diver floats again. I guess that concludes that.